All right. For this rough cut, I wanted to do a little bit on information theory in the genome. And this work by Thomas Schneider is super interesting, and it basically applies information theory to binding sites. Okay, so think about it like if you know any computer programming, oftentimes you refer to a part of a computer program by an address. So like this should occur at address 579865432. And so you can refer to data at an address. Well, the problem here is that because mutations change the length of genomes, and you have various things where things aren't always in the same place every time. Recombination, all sorts of things change the order of things. In DNA, you don't have an address by number. There's not a specific position where something exists at. So instead of doing that, they organisms have DNA recognition sequences, and so this is what allows the DNA to be to have binding sites for various proteins. They find a specific sequence, and they latch onto that, and so it's the sequence that is the address. Okay, and so what Schneider thought about is that well, what we can figure out is we can figure out how much entropy there is in these addresses, and we can figure out what is the how much space are these addresses coding for. And what he figured out is that we can use this for a variety of purposes. First of all, um, we can see uh, how, how much information that a specific binding site provides, right? So we can, if we know about one binding protein and it only uses so much information to find the binding site, but there's actually more information there, we can suppose that there might be a second binding protein for that. All right, and so, but additionally, is that we can use the size of the binding site to figure out what the size of the address space looks like. And so, like, now binding sites are like you might have the same binding site in multiple different places, and so that way the same protein can find, if it has the same function in a lot of different places, it can find the same binding site um, every place that it needs to function. So anyway, let me read you. So this is an old paper, but it's actually still, I think it's still pretty relevant. It's been cited like 1,000 times in Google Scholar. So information content of binding sites on nucleotide sequences. Um, so repressors, polymers, ribosomes, and other macromolecules bind to specific nucleic acid sequences. They can find a binding site only if the sequence has a recognizable pattern. We define a measure of the information, our sequence, in the sequence patterns at binding sites. It allows one to investigate how information is distributed across the sites and to compare one site to another. One can also calculate the amount of information, our frequency, that would be required to locate the sites, given that they occur with some frequency in the genome. Several E. coli binding sites were analyzed using these two empirical measurements. The two amounts of information are similar for most of the sites we analyzed. In contrast, the bacteriophage T7 RNA polymerase binding site contains about twice as much information as necessary for recognition by the T7 polymerase, suggesting that a second protein may bind at T7 promoters. The extra information can be accounted for by strong symmetry found at the T7 promoters. This element may be an operator. If this model is correct, these promoters and operators do not share much information. The comparison between R sequence and R frequency suggests that the information at binding sites is just sufficient for the sites to be distinguished from the rest of the genome. And that is a fascinating statement. I'm not sure that the author recognizes how important that statement is. So basically, the organism has just enough information to distinguish binding sites from the rest of the genome. Well, what does that say? Well, the interesting thing is if you think about that from an evolutionary perspective, if you had supposed that the original organism had a smaller genome, that a common ancestor had a smaller genome, and eventually the information content grew, well, if that was the case, then the it would actually have to affect all of the binding sites because, again, the binding site is just sufficient for the sites to be distinguished. So if the number of distinguishable sites grew, well, then you'd actually have to grow all of the binding sites simultaneously. Otherwise, you'd have to have some other way to get these binding sites to match each other. And also remember that the binding site and the proteins both have to evolve at the same time. They can't do it separately because if the binding site evolves and the protein doesn't, then they're not going to match anymore. So anyway, it's just fascinating that there's this interaction. So anyway, I suggest reading this paper. It's fantastic. But there's also a newer one. It's relatively recently. Um, a brief review of molecular information theory. And he basically just gives kind of a walkthrough of this idea of molecular communication and information theory. It's kind of a review of his work, which I mean, it's really good work, and I think it's worthwhile. So anyway, I just want to do a short one. I don't want to get into all the details. These two papers contain most of what you need. So anyway, it's just a fascinating area to look into.